gas laws now. We know the relationship between temperature, volume, pressure. If we combine these laws into one law, we call that the combined gas law. So this makes sense. So let's look at the combined gas law. Okay, so we're going to use this in an example. All right, so we're going to say we have a sample of helium gas. Okay, helium gas. It has a 0.18 liters. So we have a volume of helium gas that is 0.18 liters. That's what we're starting with. So we're starting with that, so that's going to be V1. So the first thing you do when you use this law is figure out what these are. What's P1, what's V1, T1, so forth. All right, the pressure is 0.8 atmosphere. The temperature is 29 degrees Celsius. So the first parts are given to us. So that's T1. So we know V1, P1, T1. What is the new temperature going to be if the gas is at 90 milliliters and a pressure of 324.16 kilopascals? So let's write it down. We want to know what the temperature is going to be. So T2 is going to equal X. We don't know what that's going to be. The gas, the volume of V2 is equal to 90 milliliters. And the pressure, P2, second pressure. So here's how you set it up. It's the first thing we got to do. Well, first you're going to read the problem. Once you've read the problem, write out the law, write out the formula. After you write out the formula, then we're going to write down what each of these parts is. Okay, so we're solving for T2. This is what we want. This is what we're trying to get. We have P1, V1 over T1 equals P2, V2 over T2. Okay, so here we have. Now, before I start putting the numbers in, okay, so next thing I'm going to do is I have to convert these to the same units of measurement. So this side we have liters, this side we have milliliters. So if we have, so let's look at the volume. If we have, let's convert these to liters. Let's convert both sides. So we have liters here, let's make this liters. So I figure out 90 milliliters is how many liters. That's what I want to know. Now remember, going back to the metric system, based on units of 10, okay, 90, same as 90.0, right? So the decimal. Milli is a 1,000th. So milliliter is 1,000th of a liter. So a 1,000th has 3 zeros. So we're going to move the decimal 3 places to the left. 1, 2, 3. So 90 milliliters is the same as 0.009 liters. Okay, so if we're going larger, and we are here, we're going from milliliters to liters, that's going larger. Because liters are a lot bigger than milliliters. If you're going larger, you're moving the decimal to the left. Larger, left. If you're going larger, move the decimal to the left. LL, larger, left. Okay, so now we're going to change this then. So over here we have 0.09. We have atmospheres on this side, and we have kilopascals on this side. So we want to make sure we have the same units. And when you're using the gas laws, we're using liters and we're using atmosphere and Kelvin. Those are the units of measurement we use. So atmosphere we have to keep. We got to convert this to atmospheres. Okay, so one atmosphere is equal to 101.3 kilopascal. Okay, we want to know how many atmospheres are going to be this. This is going to equal. Right, well, if 1 is this, I would just take this number, divide it by this, right? To figure out how many atmospheres we have. I want to figure out how many of these will fit into this. Okay, so we're going to divide. We're going to change this P2 to 3.2 atmosphere. Next thing, when we're using gas laws, we got to use Kelvin scale. So that's the absolute temperature scale. 0 Kelvin is when there's no movements of the molecules. Molecules are not moving at all. For Kelvin, we don't have degrees. We don't say degrees Kelvin, just Kelvin. So 0 Kelvin, 0 K, is equal to negative 273 degrees Celsius. Okay, 0 Kelvin, particles are not moving at all. Okay, so the 0 Kelvin is equal to negative 273 degrees Celsius. So I want to figure out how many Kelvin is 29 degrees Celsius. We go from Celsius to Kelvin, we're adding 273. 29 plus 273 is 302 Kelvin. Okay, so I'm going to change this to Kelvin. I have what I need, except for X. This is what I want to figure out, T2. So now what I'm going to do is just plug in the numbers. So P1 is 0.8. V1 is 0.18. And T1 is 302. Okay, it's going to equal. So that's just substituting the numbers over here. P2 is 3.2. V2 is 0.09. And T2 we don't know. This is what we're going to try to figure out. So we're going to solve for X. Okay, so the first thing, you do what's in the parentheses. And whatever you do to one side of the equation, you got to do to the other side. So let's multiply these first. So 0.8 times 0.18 is 0.144. So 0.144 divided by 302. So I'm just rewriting this. So, okay, those are equals. Okay, so now we have this. The next thing I'm going to do is just divide. So I'm going to simplify this thing. We want X by itself. Now we have this. Okay, I could multiply both sides by X. So if I multiply both sides by X, this is the same as X over 1, right? Those are going to cancel. And then you have this. And to get X by itself, we have to divide both sides by this number. It is 604 Kelvin. So this is how you would solve these gas problems using the combined gas law. So the first thing, you have to read thoroughly, read the question, and as you're reading the question, find out what P1 is, V1, T1, P2, V2, T2. Which one's the unknown? Which is the one you're trying to solve for? Write out the equation and then substitute. But make sure the units of measurement are matching on both sides. And for the gas laws, you have to use liters, atmosphere, and Kelvin. So for volume, for liters, pressure, atmosphere, temperature is Kelvin.